Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing OSPF, where we will review OSPF concepts, configurations, and troubleshooting in Junos. In this lesson, we'll be doing a lab demonstration, covering the configuration, monitoring, and troubleshooting of multi-area OSPF. We'll configure a router to participate in OSPF as an ABR, review the neighborship, interface participation, and OSPF database. We'll also see how to redistribute a static route into OSPF as an external route, and see how this has affected the database. Finally, we'll force a couple of common configuration mistakes and see how to identify them using operational mode command outputs and log messages. Just like the other lab demonstration lessons, we'll be reviewing the end diagram first, then the lab instructions, and finally jump into the command line to get our hands dirty. So, let's jump on in and review the target diagram for this demonstration. In this lab topology, we have three routers, VSRX1, VSRX2, and VSRX3. The shaded ovals here represent OSPF areas, with the red shaded area here being the backbone area, Area 0. The green shaded area on the left is OSPF Area 1, and the purple shaded area on the right is OSPF Area 2. VSRX3 is configured with two virtual router routing instances, with a separate OSPF process running in each routing instance. Area 1 connects VSRX3 to VSRX1, and Area 2 connects VSRX3 to VSRX2. Both Area 1 and Area 2 are general areas. They are not stub areas. In this demonstration, VSRX2 and 3 are already configured according to this diagram. So, we'll be focusing on configuring and monitoring OSPF on VSRX1. VSRX1 has interface configuration already and management access, though no OSPF configuration is currently present on VSRX1. So we'll be seeing how we can insert this router into the network as an ABR, participating in both Area 0 and Area 1. Let's now review the instructions for this lab before we jump into the demonstration. First, we'll configure and monitor OSPF on VSRX1. We'll start off by reviewing the starting configuration on each of the three devices in our topology. Next, since VSRX1 has no OSPF configuration currently, we'll statically set the router ID and configure GE001, 2, and the loopback interface in OSPF Area 0. We'll commit this configuration and review the commands and outputs used to monitor the current neighbor relationship, interface, and database status. We'll then configure a custom metric, or cost, to be used for GE002. This is a metric that VSRX1 will apply and add to any routes which use that link in the path. We'll then review the effect this has on the OSPF intra-area routes and routing table. Next, we'll configure VSRX1 to be an ABR. By configuring Area 1 and setting GE004 to participate in that OSPF area. Once committed, we'll review the effect of this additional area configuration on the OSPF neighbors and database monitoring command outputs. Finally, we'll configure VSRX1 as an ASBR by setting a routing policy which will redistribute a default route into OSPF. This policy will apply to all OSPF neighbors, and once committed, we'll take a look at the database and routing table once more to see the effect of making VSRX1 an ASBR. That'll wrap up our configuration and monitoring of OSPF section. Then we'll move on to troubleshooting OSPF. First, we'll take a look at the OSPF statistics to get some baseline information. Then, we'll configure trace options so we can get some detailed log messages about the errors we'll be creating. The first error we'll configure is to have mismatched area configuration between neighbors. Where GE004 was previously in Area 1, we'll reconfigure this to be Area 3. And once committed, we'll take a look at the statistics once more to see how things change, as well as the trace options log file to see the log error messages that are generated. Next, we'll put GE004 back into Area 1, and this time we'll configure Area 1 as a stub on VSRX1. However, we will not have the stub flag configured on VSRX3, and therefore we'll have a stubness mismatch. Once committed, we'll review the statistics once more and the trace options log file to see the effects of the stubness mismatch. And that'll be it. Let's jump on into the devices and get started. First, we'll review the starting configuration on VSRX1. As per usual, we have very minimal configuration, the lab user and some default configuration. There's a DHCP local server configuration, though we aren't concerned with that in this lab demonstration. Moving down, we have our interface configurations with the management interface GE000 and the other production interfaces below, configured with IPs according to the diagram. Then at the bottom, we have the loopback interface configured, a static route for management access, and we've placed the VSRX into packet mode instead of flow mode. Now, let's jump over to VSRX2 and review the starting configuration there. At the top here, we also have the lab user and other default configuration present. Moving down to the interfaces, we also have the management interface GE000 and the other production interfaces below it, all configured with IPs according to the diagram, along with a static route for management. On VSRX2, however, we have a router ID and OSPF configuration already present. VSRX2 is configured as an ABR, as Area 0 and Area 2 are both present with interfaces configured. Both of the interfaces connecting to VSRX1, GE001 and GE002 are part of Area 0, and the interface connected to VSRX3, GE004, is configured in Area 2. The loopback interface is configured in Area 0 and is set as a passive interface. When an interface is configured as a passive interface, it will not originate OSPF hello packets. However, the directly attached route will be advertised into OSPF as an internal route. Finally, let's check out the configuration on VSRX3 before we get started with the configuration. Now, the beginning of the configuration on VSRX3 is just like the other two. We have the lab user configured and the other default configuration present. Moving down, we also have the interface configurations, with the management interface and production interfaces below. You'll notice that the loopback interface has two logical units configured, one for each of the virtual router routing instances configured. Moving further down, we see the management access static route at the top and packet mode configuration. Then we have our routing instances configuration with the VR11 instance and VR12 instance. In each instance, we have one of the Gigabit Ethernet interfaces and one of the loopback interfaces. Each routing instance also has OSPF configuration present, with VR11 a router participating in Area 1, and VR12 is a router participating in Area 2. It's important to note that this router is not actually an ABR, because each of the virtual router instances are only members of a single area. The OSPF instances on this VSRX only see themselves as being members of the individual areas, and therefore will not flood any LSAs between the areas. These are truly two different OSPF processes running. Now that we've reviewed the configuration on all of the routers in our diagram, let's jump back over to VSRX1 and start our OSPF configuration. We'll set a router ID, although this is the same ID that would have been selected automatically as it is the loopback address configured. We'll add the loopback interface and both of the interfaces connected to VSRX2 to be part of OSPF Area 0. Excellent, this looks good. Let's commit this configuration and review our OSPF operational information. Here, we see that we have two neighbors. Both of these neighbors are VSRX2, as can be seen by the router ID of the neighbor, shown in the ID column. From the left, we have the interface IP address of the neighbor, the interface on the local router that the neighbor is connected to, the current state of the neighbor relationship, the router ID of the neighbor, the priority value of the neighbor for the DR election, and the countdown dead timer, indicating how many more seconds before the neighbor is considered dead if another OSPF hello packet is not received. You'll notice that we entered this command fast enough to catch both of the neighborships with VSRX2 before they've come to a full state. One is in the xstart state, the other in the loading state. These neighborships are not fully formed yet, as the databases have not been synchronized yet over the neighbor relationship. When we run the same command once more, after waiting a few moments, we see that both of the neighbor relationships have now transitioned to a full state. Let's take a look at the interface status next. Here, we see the three configured interfaces in Area 0, GE001, GE002, and the loopback interface. Since we configured the loopback interface to be a passive interface, it shows as being in the DR other state. From the left, we have the name of the participating interface, the OSPF state of the interface as a DR, BDR, or DR other state. This can also be in the waiting state if it's waiting for a DR election to conclude. We then have the area of the participating interface. Since we've only configured a single area so far, all of the interfaces are showing to be in Area 0. Next, to the right, we have the router ID of the DR on the broadcast segment, if one is elected, and the router ID of the BDR on the segment, if one is elected. Finally, we see the number of neighbors seen on each of the participating interfaces. Both of the gigabit interfaces have a single neighbor, which is VSRX2. Though it makes sense that the loopback interface has no neighbors, as it cannot be directly connected to any other routers. Next, let's take a look at the OSPF database currently. Using this command, we can view the contents of the OSPF LSDB. Let's first review the columns of this output before we investigate the contents more deeply. Each line represents an LSA in the LSDB. From the left, we first have the type of the LSA entry, be it a type 1, 2, 3, 4, 5, or 7. We then have the ID of the LSA. This value is different depending on the LSA type. For a router LSA, it is the router ID of the advertising router. For a network LSA, it is the interface IP address of the advertising DR. The next column over is the router ID of the advertising router of the LSA. We then have the sequence number of this LSA and the age of the LSA. Since this lab was up and running for some time before recording the demonstration, the summary LSAs generated by VSRX2 are much older than those just recently created from the neighborship between VSRX1 and 2. The last three columns are the options, checksum, and length of the LSA entry in bytes. Now, let's review the contents of the LSDB a little more closely. Stepping through each of these entries in Area 0, we have a Type 1 LSA, or Router LSA, from both VSRX1 and VSRX2. Next down the list, we have the Type 2, or Network LSAs, from the two broadcast segments between VSRX1 and VSRX2. Note that these are showing to be advertised from VSRX2, as the advertising router ID shown is the router ID of VSRX2. This is because, as we saw in the output above, VSRX2 is the elected DR for both of the broadcast segments connected between VSRX1 and VSRX2. Finally, the last two entries are Type 3, or Summary LSAs. These are generated by VSRX2 since it is an ABR. These Type 3 LSAs are repackaged from a Type 1 and Type 2 LSA. The first being a repackaged Type 2, representing the broadcast segment between the VSRX2 and VSRX3. And the last being the Type 1 LSA from VSRX3, which was repackaged into a summary LSA to be advertised into Area 0. Let's now review the OSPF intra-area routes and see how they change after we manually adjust an interface metric. We see here the intra-area routes. These are all routes within Area 0. On the left, we have the prefix of the route entry. The key column that'll be important to pay attention to here for this demonstration is the next hop interface column here. As we see, several routes are accessible over GE002, and the 10.2.6.0/30 prefix is showing to exclusively have a next hop of GE002. Let's go ahead and manually set the interface cost on GE002 to 100 and see how this changes. When setting the cost to 100, this will affect the shortest path calculation on VSRX1. Since the cost is added to the path on ingress, VSRX1 should now see GE001 as having a cost of 1, and GE002 as having a cost of 100. Notice that GE002 is no longer listed as the next hop interface for any of the destinations. This is because of the cost. The SPF calculation has resulted in GE001 being the preferred interface for all destinations through VSRX2. In the routing table, when looking at our routes installed from the OSPF protocol, we see that the network that is directly attached to GE002 is showing as being accessible over GE001. Let's now configure VSRX1 as an ABR. We'll configure GE004 as a member of Area 1 to match up with the configuration on VSRX3. We see our new neighborship with VSRX3 is showing, though we entered the command fast enough to catch it in the loading state. If we enter the command once more, we see it's completed loading and is now in the full state. Now that the LSDBs are synchronized between VSRX1 and 3, let's take a look at how the LSDB changes. We now see many more entries in the database. Not only do we have Area 1 showing at the bottom, though we also have a few new entries showing in Area 0, since we've configured a new interface and established a new neighbor adjacency. We won't step through each entry again, though something we can take note of is that the Type 1 LSA seen in Area 1 for VSRX3 we can directly see is repackaged as a Type 3 summary LSA in Area 0 and originates from VSRX1 here. This illustrates how LSAs with area flooding scope are propagated. Although they are not directly flooded between areas, the information is simply repackaged into a Type 3 LSA and re-advertised by the ABR into the other areas. Now that we've seen the effects of VSRX1 being configured as an ABR, let's see how things change when we configure VSRX1 as an ASBR by redistributing a default route into OSPF. In order to redistribute the default route into OSPF, it needs to exist as an active route in the routing table. We'll need to first configure a static default route on VSRX1. Our policy is called ADV-default, and will have a single term in the policy called match-default. This term will match only the statically configured default route by using the from protocol static statement and from route filter 0/0 exact statement. We'll apply the policy as an export policy, since we are exporting the routing information from the routing table into the OSPF process. Using the show OSPF database advertising router self command, we can see all LSAs contained in the LSDB which originated from VSRX1. At the bottom, we see the default route that we just redistributed into OSPF. This LSA is showing to be AS scope, as this is not an LSA contained in a particular area and has domain flooding scope. If we take a quick look at the routing table, we see the default route we just configured. This is showing as a static route since the preference value of a static route is lower than OSPF learned routes by default. Great. That's it for configuring and monitoring piece of this lab demonstration. Now let's move on to the last section, troubleshooting OSPF. First, let's take a look at the output of show OSPF statistics to get some baseline information. This output can give some good information on the number of OSPF packets sent and received, as well as the statistics on LSA flooding and retransmission. A key section here I want to draw your attention to, though, is the receive errors section at the bottom. This currently shows no errors have been received. Let's see how this output changes if we accidentally configure an interface in the wrong area. We'll change our Area 1 configuration to Area 3, effectively moving GE004 to Area 3. Let's also set up our trace options so we can get some more detailed information about how the device is handling this mismatch. We'll save the trace to the OSPF trace file, and we'll log the messages with the error flag at the detailed level. Great, let's commit this. And there it is. We see that we now have a receive error showing in our statistics output. We have an area mismatch. Note that this doesn't give any information about which interface or area is experiencing this error, only that the error was received. This will increment each time an OSPF hello packet is received with the mismatched information. Let's check our trace log and see what information we have there. Here, we have a lot of information showing. The key lines here are those showing that OSPF packets were ignored. Here, we see that the reason for ignoring the packet was because of an area mismatch. This trace log shows us the interface IP address of the originating router that sent the hello packet with the mismatch. and the interface and area configured on the local device. So, configuring an interface in the wrong area is a configuration issue that happens more often than you might think. Another common mistake is only configuring the stub flag for an area on the ABR and forgetting to configure it on the other routers in the stub area. Let's do this and see how that situation displays. We'll first set Area 3 back to Area 1 so that we don't have an area mismatch anymore. Then, we'll configure Area 1 as a stub. We'll leave our trace options configuration in place. We'll just clear the trace log before reviewing it again. We'll clear the trace log with the clear log command. In the OSPF statistics, we now see we have a new receive error. We have one stub mismatch. And as mentioned earlier, the area mismatch increments on each hello packet received, so we have 5 of them showing here. Finally, let's see how the stub mismatch is being displayed in the trace log. We see that this log entry is a bit more clear. We simply have the OSPF packet was ignored due to a stubness mismatch. We once again have the originating router's interface IP address and the local device interface and area which the mismatch was seen against. And that's it. This concludes the OSPF Lab demonstration. I appreciate you sticking with me to review OSPF multi-area configuration and monitoring, and to review some troubleshooting commands and outputs. I hope that this lesson has been informative for you, and I would like to thank you for viewing.